Hello, hello. Hi, everyone. Let's go ahead and start unit 2. So we're going to do two topics. We're going to do differentiation, or we're doing unit 2 differentiation. We're doing defining the derivative, and then we're doing derivatives as a function. So it's going to be pretty streamlined here. It's almost going to feel a little bit like a recap. We're going to see a lot of the unit 1 material combined with some other ideas that um are either in a place of remember this from pre-cal, or they're in a place from look at like our experience, existing, sort of that vibe. Okay. All right. So in unit 1 we learned about limits. They tell us where a graph tends to go. Limits are the foundation for calculus, and calculus is the branch of mathematics that explores motion, change, and accumulation through tools like derivatives and integrals. So we're going to talk about a couple of technicalities, the secant line and the tangent line. A secant line is a line that touches a curve. I'm just using this U shape as an example through 2 points. And then a tangent line touches a curve at 1 point. All right. And matches the direction of which the curve is going. So if it was going, for example, this way, then ideally it would go that way. Okay. The slope of a secant line can be defined like here. Recall that we are using the classic y minus y1 equals m times x minus x1. We're doing the classic linear slope, or you may have learned it as y equals mx plus b, where m is your slope, but b is your y-intercept. And we specifically are using this notation for the slope of a secant line. Now, this is going to look eerily familiar, where the idea is that we're taking the average rate of change. This is not a pre-cal topic. Um, I want to say it's a college algebra topic, but either way, the average rate of change is kind of like what it says. It's the average rate that that we change from one point to another, the point being a comma f of a to b. Here, I'm gonna actually just write that. A comma f of a to b comma f of b. Now, it's written like this, but if we take the assumption that b is ahead of a by some h, then we could technically rewrite the function like this. From here, you're only allowed to make one more simplification, and that is that these a's cancel out. So you could also just remember this as over h. Okay? Now, next, what we want to talk about, aside from this notation, is how it's going to come into play for the line tangent. So, notice how when we have these 2 points here, you could technically just sort of here. I'm gonna do it. Let me do it over here. I want to clog up this space because I don't know how much we're gonna get into it here. But if you start off with this large curve, and you take this point and this point, you can technically move the points closer together. And we can, like literally just, make it smaller. And then you bring them closer till basically they coincide with one another. And that would give you that shape of a tangent line. This is happening when you shrink zero. Or when you shrink h to 0, excuse me. And you shrink 0. Well, 0 is already small. Sorry. You shrink h towards 0, and that distance becomes smaller. So the tangent slope becomes this notation, where you start off with any point, and notice how we're technically subtracting our initial point a, so same thing, but you're subtracting it to where, or you're subtracting h, so it's smaller and smaller just till it comes a. Well, What do we call that? We basically call that a limit. Remember, the limit is the variable as it approaches a. So we're taking an analytic approach. We're saying, what is the tangent slope, provided that we're, following the trend of the curve of our f of x, of our function, and we're trending it to see what is the most accurate depiction of this curve's tangent. So that means that if we are to switch trajectory, right? So we're on the curve and we just take a screeching halt and just consistently go toward the direction. Where are we going? How are we going? And how fast, slow, and we're going to learn all these little terminologies a little bit. I think I'm accidentally getting ahead of myself, but let's just go ahead and do that limit notation. So this is defined as the line tangent to the line tangent slope. Okay, so keep that in mind. Am I missing any other definition? Okay, I'm missing this definition too. So this is our slope of the secant line, and this is going to be the slope. I'm going to just write it again. Slope of the slope of the tangent line. All right. So, let's start with the problem. Find the equation of the line tangent to f of x, which is 2x squared minus 3x plus 1 at x is equal to 2. So specifically, we're finding the tangent line at 2. So we're basically going to be filling this in. Well, let's start with our point that we're going to be at. We're going to be at, or here it's defined that we're going to be at a, but here specifically we're going to be at 2. So let's find f of 2. So that's just an easy plug and play. Um, -6 plus 1. 8 minus 6 plus 1. That's going to be 3. Okay. So the specific line that we're going to be on the curve, or point, excuse me, we're going to be on the curve is 2 comma 3. So now we need to find the slope. So the slope is defined here, but specifically we're saying a to be 2. So I'm just going to rewrite it for now. We have f of x minus f of 2 over x minus 2. Now, we already know what f of x is. It's defined for us here in this specific problem. And we also already did f of 2. So technically, we can just plug it in here. So 2x to the third minus 3x plus 1. And this was for f of x. Wait, is that a good color? I have some new colors right now. Is that a good color? And it's not that good of a color. It's pretty, but it may not be a good color. F of x, that's better. And then minus, because it's minus that 3. And that 3 is f of a. Don't forget it was a minus. Okay. So from here, I mean, we can do just the literal simplification of adding those constants on the top together. And then we're going to approach this like we would a classic limit problem. So we're going to first do substitution first to see what we get. And you may already notice that if you do substitution, if we do sub, we get 2 times 2 squared minus 3 times 2 minus 2 over 2 minus 2. The bottom 0, so we already have an issue, but let's just keep going just to, fully analyze the whole situation. And that's going to be 8 minus 6 minus 2, which is 0 over 0. So this does not work. So we need to do something. Let's go ahead and factor. Okay, so I've had a chance to look at some of y'all's notes, and I'm going to try live. I'm gonna try doing that factoring square that you all like to do, or not the you all. It's maybe not the majority, but it's just something different. So I'm gonna try to do it. I actually haven't practiced it, so let's see if I can improv this. I feel like I can. Okay. So we know that both of these have a factor of x minus 2 because 2 is a root on the top and the bottom. Well, technically it's pretty obvious here for the bottom that it's a root, but I'm just notating it. So that means we're dividing the polynomial 2x squared minus 3x minus 2 by x minus 2. The first thing that we want to make pop up in this square is this higher degree, 2x squared, which is just 2x. So we know 2x times x is 2x squared, but we know 2x times negative 2 is negative 4x. So now we need to mess with these squares so they combine into negative 3x, right? Yeah. So we know that if we just add 1x, then it would go, well, technically you're doing this square, so x times what gives you x? Well, that's just 1. And then we can fill in the blank here to double check our work, and it does indeed get negative 2. So this does match out, so we can rewrite the top. Going here, we can rewrite the top as 2x plus 1 x minus 2. Yeah. Okay. Sorry, I was a little worried about messing up that square method. And that will cancel out here. And then we're just left with the limit as x goes to 2 for just this simple expression. And here we can just do the substitution and we would get 5. And that would be your slope of the tangent line. So now let's actually get the equation. Let's actually get the formula. So we have the slope of the tangent line, and then we have the point at which that tangent line is supposed to touch 2, 3. So I'm just going to go ahead and plug this in. We have y minus 3 is equal to 5 parentheses x minus 2 distribute y minus 3, 5x minus 10, and then add the 3 to both sides. Y is equal to 5x minus 7. And that'd be your answer. Okay, so that is the idea of finding a derivative. Finding a derivative. I was reading the next line. Finding the slope of the line tangent. But what we should start to notice, and we're not going to get into it with this lesson, but we should start to notice is that this process feels like it could be streamlined just a little bit. We have to acknowledge that this is not this may be sort of tedious to do, right? Especially if we're somebody, working in a field or working in an office that cares for the like every instance of this number, because sometimes we just care about the one instance of x, so x being 2, right, in this example. Sometimes we would just care about that one number. But what we should start to notice just a little bit is that this is gonna present itself as tedious. So we need to streamline this as much as we can. We're gonna streamline this, unfortunately for you guys, we're going to streamline this gradually. So it is gonna look slow. And the shortcuts we're taking are not gonna feel like shortcuts, but we need to get used to this terminology so that when I present you all with the actual legit shortcut, um, we're well acquainted. Again, I apologize because I know that technically does not make any sense to you guys unless you've taken Cal 1 or Cal 2 before, or you've just seen a higher level math class. But I promise there's a method to the madness, unfortunately. So it's going to be a little bit annoying. Again, I'm warning you right now, it's going to be a little bit annoying, but we need to get through this. Okay, so we're going to call this idea of finding that tangent slope a derivative of a function at a point. So we call this process differentiation, and it's the process of finding a derivative. And it's using that exact same notation. Okay? where this notation is like f apostrophe of a is equal to the limit as x goes to a of that setup, basically. And this has the notation of the derivative of f of x at x is equal to a. Um, Maybe this is obvious, but I'm still going to write it just in case. The a comes from here, and it's going to be used here, here, and here. And then the f notation it's going to be the same f. So all of these three f's have them here. Okay. Actually, not this one. Or it's because like we're gonna learn that f is gonna technically be something, become something else as we do this evaluation. But the arrow doesn't make sense right now. It's technically true, but it'll make sense later. Okay. So let's start off with a streamlined version of that problem. Okay, for f of x equals to 3x squared minus 4x plus 1, find f prime, or f, well, I'm gonna start saying f prime for that little symbol there, f prime of 2. Okay, so that means that we need to fill in that limit being f2 prime of the limit as x goes to 2 of f of x minus f of 2 over x minus 2. We need to figure out f of 2 just on the side. You can do that. Okay. You could technically do that like right away, or not right away. You could do that in the problem itself. We could, don't write this down, but we could just, literally go 3x squared minus 4x plus 1 minus 3 times 2 squared minus 4 times 2 plus 1 over x minus 2. But you can see how this is sort of, oh, see, even I messed up here. I forgot to distribute the negative properly, and how it just looks a little too clunky. And we want to try to make it as streamlined as possible. So technically, what we should do is we should just on the side figure out um f of 2. So I'm gonna go ahead and do that. So we're gonna figure out f of 2 on the side. Let's use a different color. And it's gonna be f of 2 is equal to 3 times 2 squared minus 4 times 2 plus 1. Um, that first part is 12, that second part is 8, and that last part is 1, because it's just 1. And then that's gonna be 4 plus 1, that's gonna be 5. Okay. Alright. So now we can just plug that in. Minus and then 5. Okay. Okie doke. Let's go ahead and simplify this further. Subtract the 5. 3x squared minus 4x minus 4 over x minus 2. And then we're going to plug in, we're going to use, oh wait, I forgot to rewrite limit for all of these. Limit, this goes to 2. Limit as x goes to 2. And we're going to go ahead and plug it in. And let's see what we get. So we get 3 times 2 squared minus 4 times 2 minus 4. And I'm going to copy and paste a little bit of the top. We see that that's going to be 12 and 8. So 12 minus 8 and then minus 4. Yeah, so that's going to equal 0 as well. 0 over 0, which is a no-no. We don't like that. Um, Random, but looking at some of your tests because some of y'all aren't done by this time. And I'm noticing that a lot of you guys are copying the frowny face, which I fully enjoy. So thank you for that. Um, let's go ahead and then from here, because they're both zeros, we can go ahead and do that division trick again. And it's also the same root. X minus 2. we need to create 3x squared, so that's going to be 3x squared, 3x. 3x times x would be 3x squared. Times that, we get negative 6x, and then we need this square and this square to equal negative 4x, so that's just going to be a 2x. So x times what gives me 2x? Times 2. And then that and that will multiply negative 4. So this all does match. So we can rewrite this technically as the limit as x goes to 2 as 3x plus 2 x minus 2 over x minus 2. Again, that cancels out, and we're left with the limit as x goes to 2 of the expression 3x plus 2. And that's just an easy plug-in. We would get 8. So the f prime of 2 is equal to 8. All right. Okay. Now we need to talk about an application. So an application of this sort of derivative idea involves velocities. And we're recapping the idea of a rate of change. Now, we're not going to do too much applied stuff here, but you will see some. I try to cherry pick the most user-friendly applied questions in your homework. So just be on the lookout for that, please. Okay. All right. Velocities and rate change. An object is moving along a straight part, and its position at the time t is given by s of t. So s being the function it label, and t being the input, which is referring to time, which tracks, t time. The average velocity between the 2 points is noted as here. Excuse me, I burped. I hope y'all didn't hear that. I am so sorry. And the instantaneous velocity at time t is a derivative of the function position right here. So it's just going to be that derivative. Let's do an example. A rock is dropped from a height of 64 feet. The height above the ground at time t is given by this formula here, where t is going to go from 0 to 2. Find its instantaneous velocity 1 second after it's dropped. Okay, so that's referring to the technicality that s of t is our function, right? Negative 16t squared plus 64. I'm just copying and pasting. And then we're going to find s of 1 for our instantaneous velocity. 16 plus 64. Well, I'm skipping the 1 squared, and that's going to be 48. So we know the instantaneous velocity, v of 1, which is technically s prime of 1, which is that limit derivative idea. Limit as t goes to 1 of s of t minus s of 1 over t minus 1. Now I'm going to go ahead and plug it in. Limit as t goes to 1 of, let's see, negative 16t squared plus 64, and then minus 48. That's going to go ahead and be 16. Over t minus 1. Now from here, it's, we don't have to do too much work to get the limit, but I do want to go over step by step. So, we factor out this negative 16 from both sides to get t squared minus 1. And then we recall our difference of squares idea to split that top part into... Oh, I keep forgetting to write the limit. We rewrite that top part to be t minus 1, t plus 1. and then t minus 1 on the bottom. Okay. All right. And then we can go ahead and factor out the t minus 1s, and we're left with the limit of t goes to 1 of negative 16 times t plus 1. Now, from here, it's pretty straightforward that we would just use the substitution method, and we would get negative 32. Now, negative is a good thing because it is confirming this idea that the rock is falling down. So this negative means negative means the rock is falling. Um, and then the final answer can be written as v of 1 is equal to negative 32. A different notation, because we literally did not just a second ago, we were worried about using this prime notation, but in the context of this application problem, we have to address it like this. Okay? So in conclusion, the instantaneous rate of change of a function at x of a is the derivative at x is equal to a. Okay? Let me see. Uh, we also note that for this problem, it only exists the time from 0 to 2 because at 2, it's going to hit the ground. So we know that if the rock keeps falling, we didn't introduce this feature, but there doesn't exist this feature where it goes, below the surface of the ground. So just keep trick parts like that in mind. I know something like that appears in your homeworks. Okay. So this lets us move on to the next section, and it lets us streamline this derivative idea just a little bit more. So let f of x be a function. The derivative function is denoted as f prime of x, is the function whose domains consist of values of x such that the following limit exists. So a function is called differentiable, excuse me, at a if f prime of a exists. So now we're getting into the territory where we can streamline finding a derivative for any point. We do not now care about that distance of where we're looking at. We now can claim that we can find sort of just a plug and play function that will let us find that derivative of a point at any point. Okay, I lied a little bit. At any point where it's defined. Okay, that's a big thing that we get into right. Yeah, we're gonna get into in this guy right here actually. Um, so keep that in mind. Keep that in mind. Okay. All right. Let's start. So with this new definition, we're finding just the generic derivative function as opposed to a derivative at a point. We can plug and play pretty much any function and try to figure out its derivative. Let's start with this guy. So find a derivative of f(x) as it's equal to the square root of x. Okay? So that means we are f prime of x, which is equal to the limit as h goes to 0 of let me do this a bit more in steps. I'm going maybe too fast. Of f of x plus h minus f of x over h. Okay? From here, I'm going to plug in f of x plus h, and I'm going to plug in f of x. So limit as as h goes to 0 of excuse me, of the square root of x plus h minus f of x, which is just the square root of x, over h. Now, if we do substitution, that's not going to work out because we know right away we're going to get 0 divided by 0. So, what we need to do instead is to rationalize. So let's go back to classic rationalization. So I'm going to go ahead and multiply this by 1, but not really 1. I'm going to multiply it by x plus h plus x, or square root of x plus h plus square root of x over that same thing. Ah, and I get, um, I'm gonna go ahead and, I'm not gonna do distribution out loud, but let me know if I should. I haven't got any complaints about not doing distribution out loud, so I'm going to not. Okay. So that times that, which is just x plus h, and then those will cancel out, and then it's just negative x over h times square root of x plus h plus square root of x. Okay, some simplifications can occur. The first one is that those x's cancel out. And then the second one is that both the top and the bottom of this fraction share a factor of h. So that cancels out. And we're left with the limit as h goes to 0 of 1 square root of x plus h plus square root of x. Now here, it's easy to see that we can just plug in, oh, hold on, that looks super ugly. Square root of x plus h. Here we can just do the plug-in of h, and we would just get 1 over x squared, or square root of x plus square root of x, and that just simplifies to 1 over 2 square root of x. So now, if we want to find a derivative for this function at any point, we basically can. Now, I say basically because there is one point that we cannot find. Because this function, it exists, right? Like, it's right here. We see it. We got it. But what I'm literally saying is that there sometimes comes in evaluating these functions where we do break a technical rule. And if you look at this function, there is one input that breaks this expression. What's the input, you ask? I'll give you a beat. 0. If I plug in f of 0, I will not get something because I'm dividing by 0, which is, against the rules of math that we've been learning so far. All right, let's do another one. Another one. This says find derivative of f of x as e equals x squared minus 2x. Now, funny enough, this is also what I was referring to. Just real quick, just a technical recap if I forget to say it. That's why I instinctively drew the arrow here because that f is consistent. But I don't want you to think we're plugging in that f. This f creation, you see, is new, but it's just correlated. So that's why I felt the urge to plug it in. Okay. All right, let's start again. We have f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Now here you can take a beat to do f of x plus h on the side. We didn't take a beat here because it was pretty straightforward. However, these guys make it a little bit tricky, so I'm actually going to go ahead and take a beat and do f of x plus h on the side here. So that's going to be x plus h squared minus 2x plus h. Let's simplify these guys a bit. X squared plus 2xh plus h squared minus 2x minus h, or 2h, excuse me. There's no more simplification we can do, so now let's just go ahead and plug in everything. We have x squared plus 2x, I forget to write the limit again, excuse me. The limit is, over, let's see, x squared plus 2xh plus h squared minus 2x minus 2h, and then minusing f of x, which is just minus x squared minus, or no, plus 2x all over h, okay? Before we even tackle the limit, it's probably preferable if we simplify this as much as possible. So that's what I'm gonna do. Let's go ahead and combine like terms on the top. We see those x squares will cancel each other out, and we see those 2's cancel each other out. So we have 2xh plus h squared minus 2h over h, which we can literally just, factor out an h from each one of these terms, and we're left with 2x plus h minus 2. Okay? From here, I keep forgetting to write limit. Excuse me. But from here, we can go ahead and now just do the plugin, and the plugin would just make h0, so really we just get 2x minus 2. And our derivative of this function is 2x minus 2. Okay, all right. Now, we're gonna go into some more application. Not more application, excuse me, but we're gonna go into more notation that's gonna help us with some application ideas. And then we're gonna go ahead and move into more technical derivative ideas, okay? So let's go ahead and go over the notations first. So I'm gonna be transparent. This is kind of weird. Mathematicians do this thing where I think we all were developing math simultaneously. No, okay, that's a bit of an over-exaggeration, but my point is that as mathematicians are doing these notation ideas, we tend to be a bit stubborn about what notation's appropriate and what notation is consistent. I'm gonna try to stick to the usage of this as much as I can, but I know, for example, with Cal 2, and we're probably gonna get to it a little bit this semester, or maybe actually we may get more into it than I realize. Um, we also see this notation over here. Here, it's because I'm following my notes. Um, that's why I took like a random break. Where it says dy over dx. Sometimes we put the prime on the y, and then sometimes instead of writing y, we'll do d of x of f of x. So this is like that classic prime notation. These are obviously the quicker ones. It's literally just, and you're done. But these notations, annoyingly, but for a good reason, play a legitimate role. And this is called the Lebanese notation. Le, and then B. Wait, I think I had it on the first page. Yeah. Leibn. I mean, I wrote an N, but then look at N. Niz. And then the derivative at the points just has, you plugging in that specific point. If you're to use that notation, then the Lebanese, they typically write it as this. Which, it depends. A lot of this Cal 1 and Cal 2 material, frankly, is gonna be a lot of strategy, especially if you're moving up with this information. So we are teaching, or okay, excuse me, am teaching you this sort of absolute notation that is the most common that you'll see when looking at other mathematicians' work. So, of course, if you like, Is this the same notation that all mathematicians use? No. Like, I'm not even going to sugarcoat it. But the technicality I'm trying to convey is that we need to know of the other notations because they're used for ebb and flow to make things, sort of go better. So, like, just a quick insight, I this past semester taught differential equations, and in that class we straight up like flip-flop between these two notations because there was instances where this notation was preferable for the understanding of the material, and there was this notation that was just easier and streamlined. Because ultimately you can use this notation or that notation, but just some tricks, some, comprehension writing skills, um, make us want to switch between these two. That being said, I'm not gonna force you guys to stick to one or like stick or move alongside, but I think you may see it with me where these flip-flop between notations is gonna benefit you. Or at least that's like my sort of intention. Okay. Um let's okay. So that's kind of what I was saying a little bit, but this does talk about the more application side of things. How a function and its derivative are related. The graph of a function shows the height of the function at each x value. The graph of its derivative f prime of x shows the slope of the tangent line to f of x at each x. F of x can be streamlined to say where am I, whereas f prime of x can be streamlined to say how fast am I changing. So we can also use this to interpret the slope of that tangent line. If that slope is positive, then that tells us okay. So when that f prime of x is positive, the slope of f of x is positive. So the graph of f of x is increasing. A large positive value of f prime of x means that f of x is increasing steeply. When f prime of x is negative, less than 0, the slope of f of x is negative. So the graph of f of x is decreasing. And again, a large negative value of f prime of x means that f of x is decreasing steeply. When f prime of x is equal to 0, the slope of f of x is 0. So the tangent line of f of x is horizontal. The f prime values being close to 0 implies that f of 0 is either increasing or decreasing, but at like a super slow rate. All right. Differentiability implies continuity. A question that I'm technically asking you. If f of x is differentiable at x is equal to a, then f of x is continuous at x is equal to a. This is technically true. But what about the reverse? Is that true? Is f of x given that's equal to the absolute value of x differentiable? Well, let's just pretend like we were asked to find a derivative, okay? So if we're asked to find a derivative, we're going to go ahead and do f prime of x. And this is going to be equal to the absolute value of x plus h minus the absolute value of x over h. Oh, I keep forgetting to write the limit. Excuse me. Now, we obviously see the technical issue where in dividing it by, not dividing it by, but by using 0, we're going to get 0 over 0. Now, if we can move forward just a little bit, we have a technicality. The technicality being the absolute values. The absolute values in this sort of specific format doesn't really let us play with h going to 0. Okay? So, in order to differentiate this within our relative scope of what we know and don't know at the moment, right? Because technically, I know, but like I'm trying to teach it from the ground up. It's not obvious to see how we can. Okay, because like for example, we know that we can do something to where we can factor out that absolute value of x. But that does affect how h is occurring within this absolute value. So we know here at the moment, I'm gonna write at the moment, here we have basically a dead end. But look at this f of x graph over here. We noticed that for absolute value, we had a trick question. The trick question was if x was trending towards infinity and negative infinity, if x was going towards a positive value or a negative value. So, to show this a little bit better, we can go ahead and actually just propose finding the derivative of f for this function at 0. That gives us the absolute value of x plus 0 minus absolute value of 0 over x minus 0. So that simplifies into the absolute value of x divided by x. Now remember the trick questions that came about when dealing with the absolute value of x. This makes our limit, we have to ask it about both of its sides, where it's positive, where it's negative. We're technically at 0. So it's a pretty easy split to do limit as x goes to 0 from the left, rewriting the question real quick, and then the limit as x goes to 0 from the right. Here, if I perform both of these limits, we recall that because we want this to mean the absolute value, but we know that the values are going to be 0, then we have to do a double negative situation. So you have to write a negative on top of it. So negative x over x. That cancels out, and we know that that's just going to be negative 1. Here, we know that they're going to be on the right side of 0, so they're going to be positive. So we can get away with writing x over x, which we know that's just going to be 1. Now, remember our classic limit ideas. If both sides of the limit does not exist, does not exist, do not match, then that limit does not exist. So, notice how here again, how the derivative does not exist at x is equal to 0. I kind of ran out of space to what I want to write, what I want to say. Okay, again, derivative does not exist at 0. But we have to acknowledge that this function is not discontinuous. It's continuous all the way out. So, while we see here, because note technically, I didn't use it, but this function was supposed to be the absolute value of x over x. And notice how, as we approach 0, it is 1 from the right, and as we approach 0 from the left, it is negative 1. The point I want to make is, again, differentiability implies continuity. But continuity does not imply differentiability. I need to rewrite that because that was ugly. Differentiability. Oh, there's an A. There's an A. Entia. Okay. All right. Um, but to spoiler alert it a little bit, this does have a derivative, but at the moment, that's not the point of the lesson. We'll talk about it later, but that's not the point of the lesson. All right. Now, another technicality. Find the second derivative. Now what do you think the second sounds silly, like you're all there. But what do you think the second derivative means? The second derivative is kind of just what it sounds like. It's you taking another derivative. So the second derivative is denoted as f double prime of x, which is just f prime of x, and you took that prime again. So we know how to find f prime of x. In fact, that's what we're going to start off with. The limit, or here, f prime of x of the limit as h goes to 0 of, um, let's go ahead and, I think I'm going to just write it all out in one go. No, let's not. I write it out. F of x plus h. Let's see, so, because we have, here, I will streamline it a little bit. 2x plus h squared minus 3x, because I already see that the video is this video is gonna be an hour. We have x squared plus 2xh plus h squared minus 3x minus 3h plus 1. Distribute that. 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 1. Okay. So we have 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 1 and minus f of x, which is minus 2x squared plus 3x minus 1, all over h. Okay? A lot of things are canceling out. We got that guy cancels out. We have this guy cancel out. We have this guy cancels out. So limit as h goes to 0 of 4xh plus 2h squared minus 3h over h. Again, all those seem to have h inside. So we can just factor out the h. We've got 4x plus 2h minus 3. We can use the substitution, and we get 4x minus 3 as our limit, or as our derivative. So, what do you think the second derivative is? Well, the second derivative is literally just us taking the second derivative. So, if we using this notation, we can see that that is just literally going to be taking the derivative of 4x minus 3, which is another limit. So we have the limit as here, I'm going to do f double of x is equal to limit as h goes to 0 of 4x plus 4h minus 3 minus 4x plus 3 over h. This one I am streamlining it, but let me just write notation. This is f prime of x, and this is minus f of prime of x. We see here that these guys cancel out, and we're left with something really plain. 4h over h, the h's will cancel out, and the limit just becomes it became a constant function, so the limit is just trivial, it's 4. So that means the derivative, or the second derivative, excuse me, of this function is 4. Now, recall the technicality that a derivative can be a constant function. So this is goofy looking, sure, but it's not implausible. It's not out of the ordinary. Okay, this leads us to do a technicality of higher order derivatives. So typically, we can say that if we want the first derivative, we write f prime of x. Second, we'll do 2. If we do 3, we'll just do 3. Typically for 4, they stop using this notation and they'll almost write it as a power, but in parentheses. And then if they need like an arbitrary, they'll do f of n for the nth derivative. Y has the exact same feature at. And then this is a typo. It's supposed to be for the dy over dx. Because this one's a bit odd. For dy over dx, that's the first derivative. For the second derivative, let me show you the proof of it. So it's constructed like this. No, I don't need to show you this proof, but I feel morally obligated to. Um, and then we use just like sort of a multiplication trick where this just looks like d squared y over dx squared, where dx is implied as like one thing together. That's why it looks like multiplication, because for example, you would think d squared x squared, but dx is like its own notation together. So you should see it more clearly if I do, d3y dx3 for the third derivative, d4y dx4 for the fourth derivative, and then dny over dxn for the nth derivative. Okay? And I believe that's it. Yes. Okay. So let me see. So funny enough, in this next page, no, we're going to, yeah, no, it is the next page. The next page, we're going to streamline derivatives even more. But we did have to go through this notation first because it is the building block we need so we can understand the technicalities. Because once we learn these tricks, we're going to forget that at the end of the day, this is implying limits and implying continuity and things like that. So there is a method to the madness. Okay, I'm gonna go ahead and end this video, you guys. Thank you all, and again, sorry about um this being a vertical lecture only. I hope you all can understand. And let me know if you have any questions. If some of the video was bad, just be honest. Let me know. I haven't gotten too many All right, I haven't gotten any. I haven't gotten any complaints technically, but maybe I haven't seen them, so maybe that's why I defaulted to that. But just please let me know if you have any questions, guys. Enjoy the rest of your day. I'll see you all. Oh, well, I'm gonna work on a worksheet video right now, but then I'll see you all in the next one. Bye bye.